Welcome to the second module of the course Sustainable Energy Management and Efficiency for Data Centers. In this module, we move from understanding how data centers consume energy to exploring concrete strategies that can improve efficiency. The focus here is on the physical, architectural, and operational approaches that allow to reduce electricity demand, optimize resources use, and design more sustainable facilities. Improving energy efficiency is not just about lowering costs. It is also essential for addressing the environmental impact of data centers, supporting the stability of electrical grids, and ensuring that the rapid growth of digital services remains sustainable. In the following lessons, we will examine the three key areas of intervention. First, strategies to optimize the IT utilization and reduce the load of computing equipment. Second, solutions for cooling and environmental control. And finally, architectural and design considerations that enable long-term efficiency and integration with renewable energy sources. As we have seen, IT infrastructure is the core engine of data centers and a major contributor to energy consumption. In many enterprise data centers, servers operate at low utilization levels, often below 20%, meaning significant energy spent without proportional computing output. Hyperscale data centers, by contrast, often achieve utilization levels above 50%, thanks to resource optimization. The key to energy efficient IT lies in improving this utilization. One of the most effective strategies to optimize IT utilization is virtualization. In a traditional setup, each server is dedicated to a single application or operating system. This often leads to very low utilization rates, since the server's full computing potential is rarely used. Virtualization solves this problem by creating multiple virtual machines on a single physical server, each running its own operating system and application independently. In practice, this means that several workloads can share the same physical hardware, dramatically improving server utilization and reducing the total number of servers required. The benefits are doubled. Fewer servers mean lower energy consumption, and the reduced hardware footprint also lowers the demand for cooling systems. Virtualization can increase the utilization rates from below 20% in traditional enterprise data centers to well above 50% in optimized data centers. Advanced workload management is another important tool. By dynamically allocating tasks based on current capacity or energy profiles, operators can balance loads more efficiently, shut down idle hardware, and shift computation to more efficient servers. Energy-aware scheduling takes this further by factoring in external variables like electricity prices or renewable energy availability. For example, non-critical tasks might be scheduled during periods of low grid demand or when solar generation is high. Similarly, idle management strategies involve placing equipment into low power states or turning off unused resources, which can substantially reduce the baseline consumption. Another similar strategy is hardware right-sizing, which consists in selecting equipment that matches workload requirements. Over-provisioning results in unnecessary power drawing and underutilized assets, while careful capacity planning ensures optimal use. As we will see in the next module, data center operators are also increasingly using AI and machine learning to optimize IT efficiency. These technologies help predict workloads, monitor thermal conditions, and dynamically adjust servers settings to minimize energy use. AI-driven orchestration can rebalance workloads in real time, identify underperforming nodes, and recommend hardware decommissioning or consolidation. Another important aspect of IT optimization involves the lifecycle management of hardware. Regular audits to identify underutilized or obsolete equipment help avoid energy waste. Older servers tend to be less efficient, and replacing them with newer, more efficient models can result in substantial savings, especially when combined with consolidation. Moreover, optimizing IT utilization also includes considering the architecture of the software itself. Applications designed to scale horizontally, tolerate latency, and distribute computation intelligently can make better use of underlying infrastructure. Developers can support data centers' efficiency goals by writing energy-aware code, reducing memory footprints, and avoiding unnecessary compute loops. Networking infrastructure also contributes significantly to IT-related energy use. Routers, switches, and transmission systems also consume close to their peak power, even at low traffic levels. Approaches such as traffic engineering, energy-aware routing, and adaptive link rates can reduce unnecessary consumption. For instance, network devices can be placed into low-power modes during periods of low activity, or transmission speeds can be dynamically adjusted to match current demand. Emerging architectures such as optical switching and hybrid designs are showing promising reductions in both costs and power used, compared to conventional topologies. From a broader perspective, improving utilization has a systemic benefits. Higher efficiency reduces operational costs, lowers the carbon footprint, and improves the power usage effectiveness by minimizing the proportion of energy lost to idle infrastructure. These strategies illustrate that optimizing IT utilization is one of the most impactful levers for reducing energy use in data centers, often without requiring major capital investments. By making better use of existing assets, operators can reduce energy consumption, extend hardware lifespans, and improve sustainability. The next lesson will focus on another major load within data centers: cooling and air conditioning.